The first nuclear bomb was detonated in the desert of New Mexico on July 16, 1945, just 3 weeks before Hiroshima and Nagasaki. The name of this first nuclear test was Trinity. How big was the Trinity explosion? The films are great, but they are a bit overwhelming. Pictures are more useful to get a first impression. Here we see an overlap of a few pictures within the first few milliseconds and seconds, and they are placed next to the Empire State Building to stress the enormous scale of the explosion. How big is the explosion depends on when do we ask the question. These pictures were among those declassified in a report by Julian Mack, published in 1947. Mack was the head of the optical team at the Trinity test. From the point of view of physics, or mechanics, asking how big was the explosion is wondering about its yield, that is its energy, E. The energy of the bomb was kept secret, but a guy found a pretty simple way to estimate it just by looking at the extension of the blast over time, which he could get from the published pictures. That guy was the British physicist Jacques Taylor. In 1945, Taylor was 59, and an authority on a number of fields from aerodynamics to fluid and solid mechanics. He was even one of the few invited to the Trinity test, among a very short list of distinguished visitors. This video is the first of a mini-series on the physics of explosions, from tiny laser-induced explosions to nuclear bombs and even supernovae. In this episode, we will tell the story of Taylor and Trinity. The goal is to illustrate a method, an outlook on nature, which requires very limited mathematical background while being surprisingly effective. This whole channel is dedicated to the promotion and advancement of this method, and the story of Taylor and Trinity is a classical introduction to it. Taylor had been involved in the top-secret British and American nuclear programs, and in 1950 he was cleared to publish his analysis of the formation of a blast wave by a very intense explosion. The first paper was adequately titled Theoretical Discussions, and the second was concerned with an analysis of the pictures obtained during the atomic explosion of 1945, codenamed Trinity. The second paper relied on the insight from the first, but these insights are sometimes hard to decipher behind a profusion of frightening equations. Behind this mathematical show of force are quite uncomplicated but profound ideas about the relationship between motion and the mechanics at play behind it. Taylor remarked that in the first few milliseconds of the explosion, the pictures showed a quasi-hemispherical blast, extending away from the location of the bomb. On each picture, we can extract a radius. This radius gives the size of the explosion at a given instant. We will use the symbol d for this variable size. D is a function of time. This is the blast after 6 milliseconds, 16 milliseconds, 25, 53. The front of the explosion moves away at a rate that we would like to understand better. And this is what Taylor did. This is the table of numerical values he provided in his second paper. From this table of the size of the blast over time, he could get a plot like this. Here are a few illustrated data points. The more we go away from the explosion, the more the curve bends down, so to speak. The blast decelerates as time goes by. The instantaneous speed of the blast is the derivative of this curve, giving the slope at each point. How the speed evolves over time would look like this. Should we understand the dynamics of the explosion as exhibiting two separate phases, one initial fast phase and one later slow phase? But how could we define the boundary between these two hypothetical phases? When data points bend like this and do not follow a straight line, it is often a good idea to represent them on the logarithmic scale. With this representation, the dynamics actually look like a single trend, a single phase, a line. A straight line in logarithmic scale is what is often called a power law. On the linear scale, the numbers on the horizontal and vertical axis are evenly spaced. For instance, moving up from one tick to the next along the vertical axis involves adding the same amount, and the principle is the same on the horizontal axis, although the added number is different. On a logarithmic scale, adding is replaced by multiplication. For instance, along the horizontal axis, moving from one tick to the next is done by multiplying by 10. Note that on such a logarithmic scale, the minor ticks are not evenly spaced, because they recall the spacing from addition of the linear scale. Take for instance the vertical axis. These numbers follow a linear progression. We add 10 each time we're moving up to the next tick. But whereas adding 10 produces a large distance between 10 and 20, this gap shrinks as we approach 100. This is because, from the point of view of multiplication, the distinction between 10 and 20 is greater than between 20 and 30 or 30 and 40. To go from 10 to 20, we multiply by 2, whereas to go from 20 to 30, we only multiply by 3/2, that is 1.5. On the logarithmic scale, it is the progression of the exponents that is linear. Any number can be understood as given by the base 10 raised to the appropriate number. For instance, 20 is equal to 10 raised to a power around 1.3. This exponent, or power, is also called the logarithm of 20. This is why this scale is said to be logarithmic. The value of the exponents, or logs, depend on the base or radix chosen. Here it is 10, and so we can specify it when necessary. If we use the exponents of the base 10, the logs, we see that they are indeed evenly spaced. In such a logarithmic scale, the data analyzed by Taylor mostly follow a straight line. So the values of the vertical axis are linearly related to those of the horizontal axis. Log d equals log t times alpha plus a constant c. Alpha is here the slope of the line. This equation can also be written directly in terms of the size d and time t, by using each side as exponents of the base 10. Adding exponents is like multiplying, and 10 to the log 10 of d is just d, and 10 to the log 10 of t is t. So the slope of the line in log scale is now an exponent, alpha. We've transformed multiplication into exponentiation, and addition into multiplication. The factor 10 to the power c is still a constant, which we can call k. And we put it in the front because we like it better this way. This is what is called a power law. The value of k sets the vertical position of the line, but does not change its angle. The value of alpha modifies the angle and shifts the position as well. Power laws are found everywhere in nature, and we will have many opportunities to see this in other videos. For now, we can say that it is at least relevant to the Trinity explosion. If we fit all data points gathered by Taylor by a power law, we find alpha is equal to 0.41 and k is equal to 598. But you may say that the first data point seems a bit off, and if you leave it out, you would get alpha is equal to 0.39 and k is equal to 552. But 598 or 552, 0.41 or 0.39, how can we interpret these numbers anyway? The first thing to do is to take a closer look at the units. In Taylor's plot, the size was measured in meters and the time in seconds. But you will agree that one could have used yards and milliseconds, or even less conventional choices like miles and hours. Changing the units do not change the shape of the plot, just the numbers at the bottom and on the left. We said that meters, inches, feet, yards, miles, and many more similar units all have the dimension of length. You can go from one unit of length to another just by multiplying by conversion factors. For instance, 1 mile is equal to 1,609.34 meters. Similarly, milliseconds, minutes, hours, days, all have the dimension of a time or duration. We write that bracket meter equals bracket yard equals bracket mile equals capital L. You can read the brackets as saying the dimensions of, say, meter is capital L. where capital L is the generic name for the dimension of length. Similarly, the dimension of seconds is the same as that of minutes or hours, namely capital T, the generic dimension of time. We'll have more opportunities to discuss units and dimensions in the future. Let's assume for now that we agree that d and t have different dimensions. The dimensions of the size d is capital L, and the dimension of the time t is capital T. If size and time are connected by a power law, d is equal to k times t to the power alpha, what is the dimension of k? Using the bracket notation, we have the dimensions of k are equal to the dimensions of d over the dimensions of t to the power alpha. So the dimensions of k are L t to the power minus alpha, and t minus alpha is just a shorthand notation for 1 over t to the power alpha. Alpha has no dimension. The prefactor k of the power law has dimensions that are a mixture of length and time. For instance, if we take all data points into account, give d in meters and t in seconds, the fit would lead to k is equal to 598 meters per second to the power 0.41. How do we make sense of such a quantity? We say that k is a kinematic quantity, depending solely on space and time. There are a few well-known kinematic quantities mixing space and time. The most well-known is speed, which has the dimension of length over time. So the dimension of speed are L t minus 1. Another well-known case is acceleration with dimension L t minus 2. And there are others, like diffusivity. For the speed, alpha is equal to 1. For the acceleration, alpha is equal to 2. Here, we have alpha close to 0.4. What to make of that? What we know is that as soon as we assume d and t to have different dimensions, the exponent alpha of the power law and the prefactor k are connected by the mixed dimensions of k. They are not completely independent. The next step is a bold step. The idea is to assume that the kinematic prefactor k of the power law can be understood from the mechanics at play behind the kinematics. That there exist underlying mechanical quantities with dimensions beyond those of space and time. We will have plenty of opportunities to come back on this old and profound idea, but for now we can visualize it as saying that the kinematics that we can observe, here the blast radius of a time, these kinematics are really just a slice of a larger mechanical world. Let's illustrate this with Taylor and Trinity. Taylor went through the trouble of computing and plotting a curve of the blast radius of a time in order to estimate the energy of the bomb. But what is energy anyway? The standard unit of energy is the joule, with 1 joule is equal to 1 kilogram meters square second minus 2. What are the dimensions of energy then? The dimensions are m, L square, t minus 2. The capital M here stands for the dimension of mass, which from the perspective of kinematics is the stereotypical extra dimension, a dimension beyond those of space and time. We will say that energy, E, is a mechanical quantity. Generally, quantities with the dimension of mass and some combination of length and time are mechanical quantities, or mass-carrying quantities, since they carry a dimension of mass. The energy is an example. The force also belongs to this category, and of course, the mass itself, for which the exponents x and y are just 0. The only thing we are observing is how a radius changes over time. There is no mass in either the radius d or the time t. So how could the energy E fit in the equation d is equal to k times t to the power alpha? There is no dimension of mass in k. If the kinematic quantity k is to depend on the mechanical quantity E, it must do so in such a way that the dimension of mass in E cancels out. The extra dimension must be a dummy dimension. The mass dimension serves as an intermediary in the computation of k, but should disappear in the final result. No kilogram in the units of k, d, or t. Could the kinematic prefactor k and the energy E be related by addition? No, they are like apples and oranges. And subtraction wouldn't work either. One cannot add or subtract apples and oranges. Such admonition can be felt quite negatively if not followed by its corollary. One may multiply or divide apples and oranges at leisure. This last option is the standard approach for the relationship between kinematic and mechanical quantities. The idea is to introduce a different mass-carrying quantity Q facing energy, defined by its relationship with the prefactor K. K is equal to E divided by Q to the power beta, where the exponent beta allows more freedom than a simple division, and where the quantity Q has dimensions mass, length to the power x, and time to the power y, where x and y are not yet known. So let's recap. The observation is that the data pretty much follow a straight line in log scale. So they seem to agree with the power law, d is equal to k times t to the power alpha. If we assume that the size and time have different dimensions, capital L and capital T, then the dimensions of k are L, T minus alpha. Then, one way to say that k depends on the energy E is to assume that k is equal to E divided by Q to the power beta, where the dimensions of energy are known and those of the additional quantity Q are yet to be determined. Putting everything together, the dimensions of the kinematic prefactor K must match the dimension of the mechanical ratio. Obviously, the mass cancels out, leaving only time and space. The exponent of the two kinematic dimensions then give relationships between the unknown x and y of the dimensions of Q and the exponents alpha and beta. The dimensions of Q should be such that x is equal to 2 minus 1 over beta, and y is equal to alpha divided by beta minus 2. Inverting, this gives alpha is equal to y plus 2 divided by 2 minus x, and beta is equal to 1 over 2 minus x. In other words, assuming E plays a role, choose Q and get K and alpha. If the dimensions of Q are known, alpha and beta are known. And so not only Q is known, but it is associated with a specific value of the exponent alpha. This is why the mechanics are said to explain the kinematics. Because energy is understood as the motor of the explosion, beta is expected to be positive, so larger values of energy would lead to higher values of the prefactor K. In contrast, the quantity Q must impede motion. Larger values of Q would lead to a slower expansion of the explosion. A priori, a lot of factors could resist the explosion, including the mass of the bomb, the ambient pressure around the bomb, even viscosity or gravity. Taylor's great insight was to see that for the time range described by the picture he analyzed, the main resistant factor at play is the ambient density, that is, the density of the air surrounding the explosion. We use the symbol ρ for this density. Density is a mechanical quantity that is comparatively simpler than energy, since its dimensions do not depend on time. They are m, L minus 3. For normal atmospheric conditions, the density ρ is around 1 kilogram per meter cube. Then, using x is equal to minus 3 and y is equal to 0, we can solve the system of equation provided by matching the dimensions to get alpha is equal to 2 over 5 and beta is equal to 1 over 5. So Taylor's prediction for the extension of the blast radius is d is equal to E divided by ρ to the power 1 over 5 times t to the power 2 over 5. Later, we shall call this Taylor's regime. It is an example of scaling law, which is a power law where the prefactor and exponent are understood from underlying mechanical quantities. For the Trinity test, as we can see, the data do comply to this scaling, with k is equal to 583 meter per second to the power 2 over 5. Taylor was also pretty satisfied with such result, and use k is equal to E divided by rho to the power 1 over 5 to estimate the energy of the bomb, as E is equal to rho times k to the power 5. Plugging in the numbers, this gives E around 8, 10 to the 13 joules. And for bombs, energy is more often given in TNT equivalent, where 1 ton of TNT is roughly equal to 4 billion joules. With this unit, the energy estimated by Taylor is around 20 kilotons of TNT, which is indeed within the margin of error of the official value. Not only did Taylor scaling capture the blast of Trinity, but the same arguments can be applied to a very large range of explosions, with vastly different values of energy and density. For instance, tiny laser-induced explosions, with energies around 1 joule, can proceed in essentially the same way. Even supernovae exhibit the same dynamics on a truly enormous scale. Here, the pictures actually correspond to different supernovae, but we'll talk more about this another time. Taylor's method is striking for its efficient simplicity, but it also raises a number of issues. How did Taylor know that the density of the ambient air was the right quantity to be faced with the energy? How does the dynamic change at shorter time, or longer time, beyond the data points used by Taylor? What about the mushroom cloud? Those who already know this example from textbooks may also complain about the use of a strict equality here, instead of a more prudent approximation. We'll get to this soon. More on all of this in the next episodes.